Just a little housekeeping here. Admit all these. We're going to be recording this, and you'll get a link after the meeting of the recording, so you can share it to whomever you'd like. Whoops, sensitive. Pardon me. Like I said, I'm admitting people while I do this. If you'd like to arrange a meeting about this for your organization, just contact me at the end of the presentation. If you'll hold your questions to the end, a lot of times the questions will be answered at the end. You can chat it in, and we'll deal those questions at the end. I'm down in Boca Raton, Florida, in my office at my home. I'm on an AT&T fiber connection, and so consequently, the connection should be excellent. If for some reason I lose my connection or something goes wrong, stay in the meeting. I'll restart this up, and we will continue the meeting. Okay? So let me just see here. We got anybody else? One more. We've got to admit them. Okay. All right. So we are going to get started, and I want to thank you all for being here. So here's our agenda. What we're going to do, pardon me, people keep rolling on in here. What we're going to do is we're going to talk about the research that was done in the 1990s on pinhole leaks in polypipe. After that, we're going to look at failure analysis, and the failure analysis in turn corroborates the research that was done by the Gas Research Institute. PHMSA it has a no grind rule, and it was designed to address the issue, pardon me, of pinhole leaks in poly. And we're going to talk about the implications of that to the distribution market. We're going to then review the field tests demonstrating the prevention of pinhole leaks. And so that's the agenda today as we go through this. All right. Now, spoiler alert. You know, just like somebody says, I go, a great movie, and they tell you the end of the movie before you see the movie. I'm going to tell you the end of the movie before you see the movie. And that is the conclusion of the research that was done by the Gas Research Institute on pinholes back in the 1990s. And their conclusion was that these pinholes were actually caused by static electricity. And they said this. They said that what happens is a charge builds up on the inside. Pardon me, a charge builds up on the inside wall of the pipe due to the friction of the gas passing through it. And if that charge gets high enough, what it does is it exceeds the insulating strength of that plastic, and it arcs through the pipe wall in order to ground itself. And in doing so, it burns a small hole in the pipe. Now, that was their conclusion after the research was done. Now, I want to make sure, since I've spoiled the movie now, I want to tell you, though, to make sure we're all on the same basis and we all understand the same terminology. What's static electricity? People think static electricity is some kind of inferior electricity to the electricity that's in the wall here that's powering this computer. That's not the case. Electricity is electricity. It's energy. And so what happens is that energy builds up inside that pipe. And these static charges are caused by friction. What happens is static electricity is an electrical charge that has been developed because the friction of the passage of the molecule has mechanically just scraped off an electron from that molecule. And in doing so, that orphan electron starts to accumulate in random places. We don't know why it accumulates in certain places, but it does. And so what happens is that occurs, the static buildup occurs because these stray or orphan electrons are sitting on an electrical insulator, in this case, polypipe. So when the molecule of gas goes through, the friction, the scraping action, the shearing action of the molecule passing against the pipe, an electron gets sheared off and becomes an orphan. They start to accumulate in random places inside the pipe. And so that's what it occurs. That's what causes static electricity. Okay. Now, and so what this caused by is that static electricity is caused by that friction. That is the energy that causes static electricity. Now, What I'm going to show you here is a demo video we did. We make a product, an aerosol static suppressor. This video is designed to show its effectiveness, but that's not why I'm showing you this. I want you to see how easy it is for static electricity to be generated on poly pipe, because that's what they say the problem is. Pardon me, I keep admitting people. So I want you to see how easy it is to generate static electricity on poly pipe on the outside, because that's what's occurring on the inside of the pipe. Now, before we start, you see there's a meter there. There's a little electrostatic meter on there. Now, the problem with static electricity is you cannot sense static electricity. You can't see it, feel it, smell it, taste it, touch it. You don't have the sensory capacity to do that. So they make meters out there that sense an electromagnetic field or sense the static electricity, because when you have a pile of electrons, it throws off an electromagnetic field. So you can't see it, but at the bottom of that meter, there's a metal plate. So I've affixed it there. And what I'm going to do in this video is I'm just simply going to rub this pipe. See if I got this before. There we go. So I'm going to rub this pipe with some nylon. And I want you to see how fast that meter senses a charge has been built up. Now, again, and when we spray our aerosol, you see the charge is dissipated. You see how easy it is to build a static charge with friction on the outside of a pipe. That is what's going on the inside of your pipe, okay? Now, so the first thing that occurs is static electricity starting on the inside of the pipe. That's where the energy is. That's where the friction is. And GRI, the Gas Research Institute, they came to that conclusion. They said, you know, it's the passage of gas inside this pipe that's creating the charge initially on the inside of the pipe. Okay? Whoops. I have a very sensitive mouse here. Now, this is just a simple illustration. As you shear off those electrons, and I say they start to accumulate in random places on the inside of the pipe, what occurs then is they start to get in these places. And remember, this pipe is buried in earth and ground, which is universal ground. So what happens then is if that charge gets big enough, it's going to arc through that pipe wall and burn a hole. And that's what causes your pinhole leak, because by nature, all of nature wants to be at electrical neutrality. If a static charge builds up in the sky in the summer due to the hot and cold updrafts and downdrafts of the wind, the air in the summer, then what happens is that charge eventually wants to dissipate itself, and it goes and it arcs to ground to neutralize its charge. Okay? Now, that's what's going on inside a poly pipe when you have a pinhole. It is actually an electrostatic pinhole. That's what GRI says is the cause. Now, this is an important slide. People say, well, how do you know it's not manufacturing defect? How do you know it's electrostatic discharge? This is an actual electron microscope sectional of a electrostatic pinhole leak. And there's several things that's very important to notice about this. First of all, you see the black center, the black channel in the center. The reason it's black is because it's burned. What happens is when the charge builds up on the inside of the pipe and it gets high enough to overcome the insulating property of the plastic, what happens then is it arcs through the pipe wall. The heat of the arc grounding itself through the pipe wall burns the plastic. And that's the reason you see black there. If this was a normal leak, let's say a manufacturing defect, you would simply have some kind of channel in there, but no black. There would be no burn. There'd be some kind of failure. And again, if it's a manufacturing defect, notice the shape of this. They call it the morphology. Take a look at this. What's happening is that this is filigreed. You're seeing, it looks like a miniature lightning bolt from the inside going out. And that's exactly what's happened. You would not find that in a manufacturing defect. You'd see a crack. Maybe you see a bubble in there where somehow or another air got inside that in the resin and in turn caused it to breach and fail because of the pressure. You wouldn't see a filigreed action like this. You'll also see on the inside of the pipe, you're going to see a hole. And on the outside of the pipe, you're going to see a hole. That's creating the leak. But you'll see, and on the outside of the hole, if you don't clean it before you take it out, you will find a little black dot there where the plastic's been burned. Now, a lot of times when guys take it out and they clean it, unknowingly, they wipe away the evidence, they can't find the hole. But if you look, you'll find a pinhole there, a black dot where it was burned when the charge went from the inside out. Okay? So this shows you how it can't be a manufacturing defect. Now, GRI, in their research on this back in the 90s, said this occurs in everything. He says this is even under normal operations, you can get pinholing, electrostatic pinholing, because of turbulent flow. It's not bad engineering. It's not defective material. It's simply the nature of two electrical insulators, methane and polyethylene, are rubbing against each other when you compress that and transport that gas to your customer. Now, let's take a look at a couple of forensic failure reports on polyethylene pipe that was pinholed. And the first one here was done in 1989. This was prior to when Gas Research Institute was asked by the gas industry to investigate electrostatic pinhole, to investigate pinholes, because they didn't know what they were. And this was a paper written by Mark Staker, presented to the Plastic Pipe Symposium, about pinhole leaks that he found in his poly pipe. And he noticed that after he did repair, they did squeeze off, and after they did the repairs and released the squeeze off, they had pinhole leaks in the pipe from after the repair operation. They couldn't figure out what's going on. And basically, when they investigated, they sent it. It was Aldo pipe. They sent it to the DuPont lab, and the DuPont said, what happened is in the squeeze off process, the velocity picks up, the friction picks up inside the pipe. It exceeds the insulating capacity of the pipe, and it arced through the pipe wall. We recommend to all our customers, you always do soap off, and you soap your pipe after squeeze off and repair operations to make sure that you have no pinhole leaks after repair operations doing squeeze off. Okay. So here's the conclusion. DuPont lab, they said there was nothing wrong with the pipe. It was manufactured in spec. The cause was electrostatic, internal static, arcing through the pipe wall. United Cities, which is now Atmos, had the same problem. They were getting pinhole leaks in an area. It was Plexco. They sent it to Battelle Labs. Battelle said it was the material breakdown was due to a static electric field. This is a paper I wrote with Ray Ward, who was a standards engineer at Memphis. We presented it at the 17th Plastic Pipe Fuel Gas Symposium. What had happened is this. They had hired a contractor to bring in a service line, this one-inch performance black pipe. And what happened was, after they put it in, they capped it, they did a pressure test, passed pressure test. Memphis came in to go install the service. They installed the service, they purged the line, and it failed pressure test. They went back to the contractor and said, bad installation, we're going to charge you back, it's pinholing. The installer, the contractor, correctly said, how could it be a faulty installation? It passed pressure test when we were done. And that's the key question when you have pinholes. When you sit there and say, well, it's defective material, if it's defective material, it's defective material. It should have shown up when you did your pressure test. Anyway, they pulled this pipe out of the ground. They did a hydrostatic test, and it had hundreds of pinhole leaks in it. It looked like one of those hoses you go at Lowe's to water your lawn. Hundreds of holes. And so consequently, they sent it to the lab. Performance looked at it and said it was internal static. In the purging operation, in the static generated in the purging operation, it exceeded the insulating strength of the plastic, and it pinholed the pipe, causing the leaks. Connecticut Natural, same thing. They were getting pinhole leaks in pipe. It was 4-inch Plexco. And let me tell you, I have a customer who had a pinhole leak in a 20-inch poly pipe. This is a 4-inch. They sent it off to GTI Labs. GTI Labs came back and said it was static discharge caused the failure and the pinhole leak. So when you look at these, here are just a sample of failure analysis of pipe that's been pinholed. You have 4 different labs. You have different materials. You have different locations all around the United States, Utah to Connecticut to Memphis, all over. Okay. Same conclusion. Electrostatic discharge through the pipe wall, not manufacturing failure. Now, we're going to talk about the rule that PHMSA promulgated in 2015. And what they basically said to pipe manufacturers is, we are concerned about pinholing in pipe, and we do not want you to put regrind or leftover plastic in pipe that you're using to make fuel gas pipe. What happens is when they make pipe like you would make a cake. You get a bin, or when you make a cake, you get a bowl, you put a certain amount of flour in it, a certain amount of sugar, an egg, vanilla, baking soda, whatever you put in. Mix it all up and you bake it. Well, they make pipe the same way. They get a big bin and they get some resin, polyethylene resin. Then they put their own formula of chemicals in it. Or maybe there'll be a colorant. They may be a UV stabilizer, and they may have some other proprietary things they mix it, all the resin up, they heat it till it's gooey, and then they start to extrude it and make the pipe. Now, when they first extrude that pipe, it's probably not going to have the correct wall thickness or diameter. It may be a little out of round. And until that machine gets up and running and all of it's the spec, what they'll do is they have to get it up going. And once they get it to spec, to physical spec, remember, the resin's all the same from the beginning to the end. There's nothing different than the beginning of the end, the quality of the resin. What they'll do is that beginning portion of the pipe, they'll cut it off, set it aside because it's out of mechanical spec, and set it aside. They'll extrude all their pipe, and when they get to the end of the batch, probably the same thing will happen. In the extruding, it'll be running low resin, and the pipe may get a little out of mechanical spec, so they stop it and they put that stuff aside. Now, the next time they make that exact type of pipe, what they'll do is they'll take that prior pipe that wasn't mechanically to spec, but chemically was okay. They'll chop it up, they'll regrind it, and when they make the next batch, they'll put this in so as not to waste it. PHMSA said, we don't want you to do that because we think it causes pinhole leaks. And here's what they said. They went and in their research, they found that there was microscopic treeing. Again, remember those pictures I showed you, the lightning and also the electrostatic pinhole leak in the pipe? You notice treeing, it looks like a tree because that's what it is. And based on these research reports, based on these reports, here's what they said. They indicated this rework could potentially be a cause of concern, causing the breakdown of the dielectric or the insulating property of the plastic and the development of pinhole leaks and static discharge. Okay? In other words, this is what PHMSA is saying. They recognize that there's an ongoing problem with pinhole leaks in polypipe, and the purpose of this is try to minimize that. Now, you may be listening to me in this, and you may have some guys and say, we don't have pinholes in your system. PHMSA does. PHMSA thinks you do. So they have a big picture in the nation, around the nation. So consequently, they're saying to them, this is an issue, and they made this rule that pipe manufacturers cannot use regrind when they make poly fuel gas pipe. Now, there's 3 implications from this. Now, the first thing is, and we'll talk about this in just a second, we're going to work into this. Just because there's no regrind does not mean a pipe will not pinhole. Every pipe will pinhole if the static inside the pipe exceeds the insulating properties. Whoops, hold on. Let me get Mr. Rogers in here. Every pipe will pinhole if the voltage inside that pipe exceeds what the pipe is capable of resisting. That is called the dielectric constant. And with medium density and high density polypipe, it's pretty much the same. It's about 510 volts per thousandths of an inch of thickness, wall thickness in the pipe. So, for instance, if you have a 1-inch yellow polypipe, okay, it has a nominal wall thickness of 120 thousandths. Multiply that times 510. And you get 61,200 volts. In other words, if the static inside that system, inside that pipe, exceeds 61,200, it's going to arc through the pipe, the heat will burn a hole and create a leak. Now, to put this in perspective, it only takes 3,000 volts, a spark of 3,000 volts It only takes a spark of 3,000 volts to generate 1,100 degrees Fahrenheit heat and ignite a gaseous mixture. Okay, so that's to put that in. Now, again, I'll tell you, I have a customer who had a 20-inch poly pipe, 20-inch poly pipe, and he had a pinhole leak in it. You do the math. You think about the voltage that was in there. Okay, so take a look at this now. What I've done is I've shown you with the breakdown what the threshold voltage is on each of the different pipe wall thicknesses. So, for instance, a half-inch pipe has a nominal 90 thousandths of a wall thickness. So consequently, at 510, and again, high-density polyethylene is a little higher, not much, maybe 10 volts, not much at all. But a half-inch pipe, if it gets to 40, because it's got a thinner wall, once it gets to 45,900 volts, it's going to arc through the wall. In three-quarter pipe, if it hits 48,450, because of the thicker wall thickness, it'll start to arc through the pipe and create a hole, and so on and so forth, right down the size of the pipe. So you can see then, logically, you're going to see your pinholes. If you have static in your system that's creating pinholes, it's going to start in the smallest diameter pipe first. And that's where we normally see it. We see it in service lines. Now, consideration 2 with the regrind rule, PHMSA's regrind rule. When they passed this rule in 2015, there was already 912,000 miles of poly pipe in there, some of which had regrind. Not all the manufacturers had regrind. Some did, some didn't. But the point of it is, there's a lot of legacy pipe out there. And the reason they didn't want the regrind in is they believe that lowers the dielectric. It makes it more susceptible to pinholing. So you got 912,000 miles of legacy pipe out there that you got to remember you have. And finally, it is more susceptible. That legacy pipe is more susceptible to a pinhole. The common denominator, both in GRI, in the failure analysis, and in PHMSA, it's static electricity. That's the root cause. That's the root cause. Now, if that is all true, if the research is right, if the failure analysis is right, if PHMSA is right, then it follows that if we suppress internal pipe static, you should stop pinhole creation. Okay? Now, about 18 years ago, the city of Benton came to us. We make internal static suppression for gas systems. They came to us back in 2013 because they were having leaks in their system. And this was way before methane emissions. See, this is pinhole leaks now, and your leaks in your system are now an issue because of the upcoming methane. You know, all the methane emissions stopped at your requirements, stopped at your city gate right now. I think personally, my opinion was that the legislatures did that to give you a buy time and allow you to get the cast iron out, get that stuff relined, to get your systems, you know, cleaned up before they put emissions. It's coming, okay? It's coming. But these guys came to us 15, 18 years ago because they were having leaks in their system, and they were just concerned they were going to have an accident, okay? And so they came to us and said, we want to put static suppression in our system to see if it'll make a difference in the leaks we have in our system. So back in 2013, what we did is we put our static suppression cartridges at their gate stations. They have 2 delivery points or gate stations. So what we did is we installed our static suppression cartridges at their delivery point that feeds their entire system. Now remember, their problem, you go back at this, you notice, remember we said, if it's caused by pinholes, your service lines, your smallest diameter pipe will pinhole first and corresponding up. As the voltage goes up in the system at different points, thicker wall pipes will pinhole. And that's what you see here. You're seeing pinholes first in your smallest service line. The next most pinholes are in the middle size, and so on up the diameter of the pipe. So what we did is we put static suppression in their system and introduced it to feed their entire 320-mile system at the time. Now, this is what happened in the intervening 6 years since we've installed it. Actually, I've got updates on this, but they saw a decline of 88% leaks in their system when they suppressed the static in there. And notice, take a look. Again, all this follows, it makes sense. It conforms to the research that was done. Notice there's virtually no leaks in the larger diameter pipe. There's a few more in the smaller and a few more in the smaller diameter pipe, which means that, you know, the bigger, the static is being suppressed in the system to the point that anything they're seeing is a small diameter pipe. Okay. Now, I happen to call this current superintendent, Todd Riley. He's the superintendent at City of Benton. Feel free to call him because they wanted to share this. We have other customers that have static suppression in their system. They've seen the same results. We don't, unless they give us permission, we don't disclose them or what they do. But Todd will be glad to tell you. But I called him because I said, you know, how it's been. I haven't updated this in a little while. And he sent me an email and he said, we have not had any static leaks since 2020. Okay. For 3 years now, they haven't had any static leaks. Okay. Now, note, he doesn't say he didn't have any leaks. He said he didn't have any static leaks, any pinhole leaks. So the research is right. Internal static causes pinhole leaks. If you suppress them, then you can prevent pinhole creation. Now, here's what we found in them. Pinholes generally occur in your smallest diameter pipe. There's no pattern. I've seen them. I've seen service lines with 1, 2, 3, 4, 5 lines. That one in Memphis, they had hundreds of holes in it. I've only seen it at poly, no PVC. It's not limited to one brand of pipe. We've seen it in every brand of pipe, every one. You had 3 or 4 different brands just in those 4 failure analysis I gave you. They cluster. If you find pinholes in a certain area, and they're harder to find because of soil conditions, and sometimes it takes several surveys to sniff them out. But what happens is you'll find it in a geographical area. If you start to have pinholes in an area, you got more of them. You just haven't found them. And they'll continue and increase in number simply because you haven't dealt with the root cause, which is static inside the pipe. Now, this is the most important slide I'm going to show you today. I'm going to say that again. This is the most important slide I'm going to show you today. Because what this field test does, backed up by the research, it says this. There's really 2 types of leaks in polypipe. I'm going to call the first one opportunistic. They are third-party damage. That's ground shift, bad fusing. All these leaks vary in size. They vary in location. And they have different size. They have different location. They're eventually identifiable, but they're very difficult to prevent. You have 811, but you know people don't call for a locate. You know guys are supposed to be qualified in fusing, but sometimes that fusing goes bad. And those opportunistic leaks, they're very difficult to prevent. However, systemic electrostatic pinhole leaks, they're always the same size, okay? Once that voltage hits the certain threshold point, it's going to arc through and burn a hole in that pipe. And it's found in pipe. I've found it in fittings. I've found it in fusions. And it's not easily recognized because nobody really knows about it. When your guys are in the field, they think they don't have a pinhole leak. They said, well, it's a little manufacturing defect. They don't know what it is. Here's the key thing. They're preventable. This class of leaks is entirely preventable. Now, that is not something that's out of the realm of possibility. I want you to stop for a minute. And we're going to stop talking about polypipe, and we're going to talk about metal pipe. In metal pipe, you have opportunistic leaks. You have third-party damage. You have ground shift. You have bad pipe fitting. And so what happens is you're going to have different kinds of leaks based on if somebody backed into something and broke a piece of pipe, or the foundation sank, or horizontal directional drilling drilled through your line or something like that, okay? And they're very difficult to prevent. However, that metal pipe is a manufactured product and it has a high internal energy content. So when you put that metal pipe in the ground, like all things in nature, it wants to go to its lowest energy state. So that metal pipe in the ground, when you put that in the ground, that's going to want to start to react with anything around it and corrode and create a leak. You can prevent those leaks by putting in cathodic protection, and that's what you do. That class of leaks in metal pipe is completely preventable. systemic electrostatic pinhole leaks in polypipe is completely preventable. It is a preventable leak. The city of Benton found about 80 to 90% of its leaks were static caused. The balance were opportunistic. Now, again, your problem is how many of your leaks out there are electrostatic, because it's very, it's difficult to see. And most guys in the field, they don't know how to recognize it. And so consequently, the exact extent of electrostatic leaks in most systems is unknown. You just don't know how much it is. But if you're getting these leaks popping up on your survey, most likely they're smaller, fizzy leaks. Most likely are going to be caused by static electricity. Whoop. So basically, just real quickly, we're going to just talk about, just this one slide, how we do static suppression. What we do is you put our static suppression cartridge in the point upstream where you want to have downstream static suppression. I have some people, we have a lot of customers. Some people put it in a certain area. Some people put it in a gate station. You can do it any way you want. Doesn't matter. It's just you have to decide where you want to introduce internal static suppression in your system. And our system is sized by the pipe size it goes on and the pressure. And all you do is install a housing which holds our cartridge. And what happens is when the gas passes through our cartridge, it's not a filter, okay? When the gas passes around the core of our cartridge downstream, it automatically dissipates any static present and prevents its buildup. And it works automatically. You don't have to do it. Now, there's an added benefit, as you're going to see in a minute when I get to the very end. There's an added benefit of putting static suppression in your system. It reduces ignition and shock risk. We'll do that in a second. And here it is. Dave, Zach, and I do a seminar on the 8 priorities of responding to a natural gas emergency. And he shared this slide with me. Dave, Zach, spent 20 years at Ameren, and he's the senior utilities loss consultant for Ameren. He goes around to gas companies and teaching them how to prevent losses. And he shared this slide with me. Now, when I teach the class static electricity at the Northeast Gas Association's Gas Operations School in Rhode Island every summer in June. I'll do it this summer. And I'll poll the class. These are guys, field guys and managers. And I'll say, okay, guys, have you ever seen an injury based on an automotive injury on your being out in the field? 3/4 of the class raises their hand. I said, okay, how many vehicle accident? 3/4 of the class will raise their hand. How many of you seen where there's been some environmental damage? You'll make 50% of the class, okay? How many of you have seen any CO2 poisoning or contamination? Maybe 5 or 6. How many of you seen a fire or explosion? Maybe 2 or 3 guys will raise their hand. So I say, okay, based on this survey, really, if we're going to have loss prevention and prevent losses in gas operations, what we want to do is focus on vehicle safety, right? Wrong. This is the chart of what Aegis pays out in claims to you guys. Aegis insures 99% of you guys out there. They co-insure with you. This is where they're paying. They pay almost 80% of their claims on explosion or fire. Where should you concentrate your efforts to prevent loss and injury? Stop the ignition. Where's the ignition coming from? Think about that. This was a slide sent to me by Fire Findings newsletter. Fire Findings newsletter is a newsletter circulated among fire investigators to share what they found when they have a fire, so they can share the knowledge to prevent it with other investigators. And they sent this to me because they were having a problem. They said, we're getting all these fires at gas service meters and we can't find a source. Could it be pinhole leaks in the service lines that caught fire and that's what caused the fire there? Take a look. You see that? There's no line coming down. It's burned away. You bet. You bet. I had a gas gatherer out in Southwest United States call me up. And he called me and he said, Dirk, I want to, something happened and I want to tell you what happened. He said, we got a call from this. He had a gas well. He was an operator. He had a gas well. And he said, we had a well. We got a call from the local fire department. They said, one of your wells is on fire. So we go out to the well. Now, at every hydrocarbon well, when the product comes out of the ground, it goes through a phase separator. They separate the gas, the water, and the oil. Every well has that. Every well has oil, every well has gas, and every one has water. So the first thing they do when they collect the material out of the well is they separate it. And what had happened is on that phase separator, when the lines come off that phase separator, they had polypipe. One line was carrying the oil, one car was carrying the salt water, one line was carrying the gas. And what had happened is the gas, the poly coming off the gas port on the phase separator completely burned away, and a fire had erupted and was just burning the gas from the outlet of the gas outlet on the phase separator. And he said, could it be polypipe? It pinholed and then caught fire? You bet. What other excuse? If it was lightning or something, the oil line would have gotten hit too, or you would have seen more damage. This problem of pinhole leaks has been around for a while. So I'm going to review the final things here. You have really two types of leaks, not one type, two types, just like you have two types of leaks in metal pipe. You have two types. You have opportunistic, and then you have electrostatic and electrostatic pinhole leaks, electrostatic leaks. And the electrostatic pinhole leaks are generally misidentified because they don't know how to recognize them. It all started by the passage of gas inside the pipe. That's normal. Friction builds up. It's not unusual. It's just natural physics. It's created by normal operations. I found them in every brand of pipe. There's nobody's immune from it. All the date, unless you have a different failure analysis that I've not seen, all the failure analysis indicates that internal static caused that pinhole leak. That if you external methods will not solve the problem inside the pipe. You have to deal with the problem inside the pipe. Only internal static suppression will prevent pinhole leak creation. Pinhole leaks are an emissions and an integrity issue. They're both. One last thing. If this is true, all this is true, then other areas in the petroleum and gas industry should experience the same problem. In other words, in the upstream gathering market, they should have the same problem. I remember about 5 years ago, I was talking to a major pipe manufacturing poly salesman, and we were at a oil and gas show. And I said, you have any pinhole leaks in the upstream market and gathering? And she said, nothing I've heard of. Well, and I kind of thought, gee, that's odd because I'm seeing them in the downstream market. And then last year now, all these upstream guys are now required to leak survey for the first time. See, you've always leaked survey. Okay, you've been required to leak survey. They were never required to leak survey. And with the Inflation Reduction Act now, they're required to leak survey in their lines. Guess what? They are finding a ton of pinholes in that upstream poly pipe they never knew they had because they never had to deal with it because they never had to leak survey it. And I'm getting a lot of calls from these guys who are absolutely bewildered at the fact that they have pinhole leaks in these lines. Once again, the fact that the upstream guys are having the same problem as you in the downstream, again, confirms the original research, confirms the failure analysis, confirms what happens with Benton, that it's static inside the pipe. And anecdotally, from my conversations with them, they're having more pinholes than you are. Anecdotally, it seems that way. So, internal static suppression is the poly pipe, a cathodic protection is the metal pipe. That's really the bottom line. So, that's it. That is what I've got for you today. We're a little ahead of schedule, and I'm glad your time is valuable, and I hope it has been useful to you. If you have questions, if you want to do some questions, feel free to chat me some questions, or if you want to hit your audio and ask me a question. Otherwise, you'll get a link afterwards with a recording on this, and I'll be glad to answer any questions or anything you have. Well, am I missing anything? Okay. Well, okay, everybody. If no other questions, then I'm going to finish this meeting up. Look for an email with the link on the recording so you can share it. I appreciate your time. And again, contact me if you have any other questions about pinholes and polypipe, and we'll be glad to answer them for you. Last call. Oh, Dave Rico. Okay, Dave.
Hi, Derek.
Yes,
Yeah,
Dave.
question for you, sir. If this can be handled upstream, how long does that static protection, I suppose, go downstream? I mean, how often do you have to put a
burner tip
filter in here?
Yeah, to burner tip. What happened in Benton, which we've had other systems, same thing. Most systems, most guys put it at a gate station. And so what happened was Benton's problem was at the service lines. We put the 2 static suppression cartridges at a gate station, and it solved his pinhole issues at the service, at the gate, at the service point, burner tip. So consequently, through the whole system, goes right from gate all the way through the whole system. Does soil have any effect in this? Yes, but I don't know. Nobody's ever done any research. I mean, this is really the forefront. I mean, you guys are on the forefront of this. This is not well understood at all. I can tell you, the upstream guys are absolutely befuddled by this. They are having a tear. They're required to pay a tax starting in 2026 on their emissions in 2024. And they've started surveying the lines, and they're getting a shock. And they're getting up there. Now, that's in South Dakota, North Dakota. I don't know what the difference is. Benton's in Kentucky. I'm sure soil has something to do with it, but no research that I know of has been done on that. I don't know. And even if they said, okay, your soil is conducive to it, you can't change the soil. You got to just, if you got the problem, you just got to mitigate the problem. Mitigate the problem. Any questions? Any other questions? Let's see. Yes, we change the cartridge once a year. What happens is we keep track of it, and in about after a year, we notify our customers and say it's time to replace it. We send the replacement cartridge up to them, and when they go in, they take the old cartridge out and they have a new one to put it in at the same time. So 20 minutes, they take the old one out and put the new one in. Is there a specific gas velocity range when pinholing is reduced or eliminated? Excellent question. Excellent question. There is no research on it. And so we're at the end and people have to leave. People will leave. But I'm going to tell you the story at Benton, what happened when they first called me. And this deals with your question, Jesse. They called me up and they said, you come up here and let's measure static in our system. I had my electrostatic meter. So I said, okay. So I go up there, and at the time, it was Kelly Collins, who was the superintendent at the time. So he took me to one of his gate stations. And what we did is on a tap, we just put a 3-foot piece of MDPE, open the tap, and we're blowing methane out at 99 pounds. We did it for 5 minutes, 10 minutes. So I said, surely I'll get static on that. So I put my meter on the pipe, nothing. He says, okay, let's go to another gate station, or another regulator station. We go to another regulator station, and same thing. We put a piece of pipe on there. We measure the static, nothing. And I'm thinking, these guys are going to think I'm nuts. He says, Kelly says, well, hold on one second. I have a friend of mine, and he let me dig an inspection trench on the service line going to his house. Now, I was up there in April, in spring, packed lines. Okay, this is summer. I mean, this is spring. There's not a big demand. It's not like winter where there's a lot of stuff. So I walk over, and here's this, inspection trench for this service, small 1/2 inch, maybe 3/4 inch service line going into the house. I put my meter down on it, and it pins the meter, pins it. Now, if you had asked me, I would have found the static in the line blowing at the regulator station, and I wouldn't have seen anything in that line because there was no velocity in that service line. The service line's where I found the static, and I didn't find anywhere in the line with velocity. I wish I had a problem with that. I'm sure velocity has something to do with it, but I think there's a lot more complicated factors involved that contribute to this, that you can't just isolate it either to soil or the velocity. It's just not that simple. As your solution to chemical or mechanical reduction device, our cartridge has a proprietary core in it. The gas passes around it. And so consequently, it just passes by it and the effect is created. Can any qualified operator change it out? That's a good question. All the, with the instructions are basically you just, you bypass it out of the system, take the old cartridge out and put the new cartridge in. And so all the operators have done it themselves. And so, they do it themselves. They don't have a problem with it. Let me see. Have I answered any more questions? Let me see if there's any others. If you put this on suppliers upstream, do they have anything for us down here? We have only put these in distribution systems because if everything normal, I'm sorry. We've only put this in distribution systems because it's all low pressure. The upstream guys are all high pressure and they're on metal. And so consequently, they don't have a pinholing problem. They have a corrosion problem, not a pinholing problem. So consequently, there's no need for them to put that upstream. So generally what we do is we put it in upstream at the gate station for the distributor, and it'll go through metal. Our process will dissipate the static inside metal pipe too. Metal doesn't diminish its performance or anything. And then of course, when it transitions to plastic, it just does the same thing. It will dissipate the static downstream. So I can't answer that question definitively because no any suppliers put it upstream because they have no need to, and they won't do it. They won't do it unless they have to. So it's usually less to the operator to be the one to install this. Okay, blast velocity. I got a couple others down here. Let me go. Yes, when you're taking static electricity reads, are you doing this externally on the pipe? I would be interested in checking this out. Now, I have people who want to try to measure and check static above ground before they put it in the system. If you see the reports like a GRI and what these guys do to measure static, you'll recognize that is a fool's errand. It is very difficult to measure static accurately because static is everywhere. So for you to measure static, what you have to do is when they do it in lab environment to accurately measure it, they put what's called a Faraday cage. Just imagine a metal screened in porch, and they put it all around it and ground it in order to make sure no stray static electricity comes in and interferes with their readings. When you take a static electricity meter reading, it is like you taking a picture on your camera. Okay. I'm looking at Deborah Hudson here. She's on a view here. So if I took a picture of Deborah and I took my phone out and I snapped a picture of Deborah, in my head, I want to take a picture of Deborah's face. But my camera also picks up the window in the corner, the bookshelves and everything like that. It can't discriminate. It picks up everything. Static is the same way. It picks up everything. It will pick up a static charge behind the pipe, inside the pipe, on the outside of the pipe. So when people say, listen, I just want to know if my problem is static, the cheapest way to do it is to take a little section where you're having pinhole. If you have pinholes, there is no doubt that it is caused by static electricity. The forensic and the research has said it's static electricity. So if you put internal static suppression in there after a year, just like Benton did, when you do your survey, you're going to know in a year that it is pinholes, and to the extent that pinholes are part of your leak spectrum. Okay. So that's really the best way to do it. I really discourage people from trying to take static readings themselves. It's very, very difficult because you really have to control the environment. You have to know what you're doing. And if you're concerned about it strictly from the point of knowing if you have pinholes, if you've got pinhole leaks, then you got static. End of story. End of story. That's it. It's all been proven. The best way to sit there and confirm it is just take one little experiment and put it in ground. Just take a little section, put it in ground and test it. Okay, let's see. Anybody else? Does the size of the static suppressor change based on how many miles of piping? No, yes and no. It's sized based at the pressure and diameter of the pipe at the point of installation. Okay. So we have some customers have 2-inch and 150 pounds going through it at 2 inches. So it's a little cartridge, maybe 8 inches tall and 2 inches wide. I've got other customers that have a 4-inch at 1480. Well, that cartridge is bigger. So the cartridges vary in size based on the diameter of the pipe and the pressure at the point of installation. Okay, let's see. Anything else? Any other questions from people? I have one here. Well, I think everybody, that is it. So again, if you have any questions or anything else, just give me a holler. If there's anything I missed, look for the email with the recording. You can share it. And I do appreciate you being with you. Your time is valuable, so I want to make sure I don't waste your time. So, and Deborah, it was great seeing you. Now I can put a face with a name. So you all have a nice day, and I'm going to sign off here from Boca Raton. Thanks so much. Yeah.